Alright guys, let's discuss carbynes. Now we've looked at carbynes, we see we're making progress. We've looked at alkyl compounds, we've looked at carbynes, and now we're going to look at carbynes. We've also looked at olefin complexes, you're working with arene compounds. By the end of this course, I think you would have had a pretty good survey of organometallic chemistry. Now what are carbynes? Carbynes are metal-carbon triple bonds. Again, we mentioned this in the 2000 course very briefly. But here's what we're going to look at today. Again, I'm going to take things slow. We're going to look really at, well, the bonding situation in Fischer and Schrock type carbynes. And we're going to look at some synthesis. I'm just going to keep it very thin today. I don't want to go into too many synthetic details. And we're going to look at alkyne metathesis. So we've just looked at alkene metathesis. You can do the same thing with alkynes using Schrock type carbynes. Now, this is a sort of a pedantic point, but when one's talking about Fischer type carbynes, one talks of a carbyne, and if it's Schrock type, you generally talk of an alkylidyne. But most people just say it's a Schrock type carbyne, but actually, strictly speaking, one should call it an alkylidyne. So it's the same thing, but it's just if it's Schrock type, it's alkylidyne. Incidentally, the same thing with carbenes. So if you're talking about a Fischer type carbene, you call it a carbene, and if it's a Schrock type system, you call it an alkylidyne, right? So that's just some formalism. Now, what are carbynes? Carbynes are metal-carbon triple bonds, and sticking now we're confronted with the same problem we had, a moment ago, where we were looking at counting electrons in carbene complexes. We have the same situation here. Now, again, the best way to do it is to think about it as a 3-electron donor. Let's do some examples before we get to this. So we'll come back to this in a second, but let's just see how we count carbynes. So this is an example of a carbene complex. This is a prototypic Fischer type carbine. And to count the electrons, counting covalently, covalent counting, chromium is in group 6. We have 4 carbonyls, so that's 8. We have 1 chloride or halogen. This is a halogen, X is 1. And the carbine, is 3. How many valence electrons do we have?
18.
18. So if you count, now for the carbines, I'm not going to look at the ionic counting because that just gets very complicated. But if you count covalently, you can't go wrong. Just remember it's a 3-electron donor, irrespective of whether it's Fischer or Schrock type. Now, just like we had the Dewar-Duncanson model this morning for carbenes, we have the same thing for carbynes. And here we have the orbital interactions between a metal and a carbine fragment, Cr, if it's Fischer or Schrock type, sticking to the covalent counting methodology, right? So we're thinking about it as in a covalent way, right? There's another way of looking at it. I'm not going to go there. I'm just not going to go there, right? If some of you are interested in how to deal with it, if it's ionic, see me after class, but I think it's going to confuse the hell out of everyone. So if it's Fischer type, we can imagine that that's the bonding situation. Very similar to what we had with carbenes. We have a donor-acceptor interaction, a sigma donor and a retrodative back bond, pi acceptor here. But you see it's a 3-electron donor. There's 3 electrons there. Now if it's Schrock type, also 3 electrons, but notice the electrons occupy different orbitals, and we have a covalent picture. So the classical difference between Fischer and Schrock, also with carbenes, is that in the case of Fischer, it's a donor-acceptor interaction, right? Sigma donor, pi acceptor. With Schrock, it's always covalent. And that's another way of understanding why the bond order in Schrock type systems is always a little bit higher. Now, let's now look at the synthesis. let's start off with Fischer. I'm only going to discuss the prototypic Fischer carbine compound because for an undergraduate course that more than suffices. Okay? How did Fischer make this? Well, it turns out he made it by accident. Okay? 1973. The same year that he won the Nobel Prize, incidentally. So it was obviously a very good year for him. My grandfather. He told his graduate student to go into the lab and to try and make this compound. I'm going to turn this off. So he sent his graduate students into the lab. Remember, 1964 they had made Fischer and Marsböll made the first Fischer carbene complex, the classic Fischer carbene. So let's write them down. MCO5 C, I'm just going to keep the general R. That's the classic Fischer carbene. And he was doing a lot of chemistry with these complexes, Fischer. He was a very clever guy. And he said, okay, that's very interesting. We have established that the carbon of a Fischer carbene is nucleophilic or electrophilic? Electrophilic. What would happen if we were to put a halogen on the carbene? That would be interesting, right? Because you've got an electrophilic center, and if you put a halogen on there, a halide, it's going to make it even more electrophilic. And he thought that would increase the reactivity of the complex, right? Because you'd make it super electrophilic. So his idea was to make this. I'm just using M, where M is a group 6 metal. His idea was to make this. In other words, to replace that alkoxy group with a halide. Obviously, that would increase the electrophilicity here dramatically and possibly enhance the reactivity. That was his idea. So he sent his students into the laboratory and said, try this reaction. And the reaction that they did is they took one of these and they reacted it simply with BX3. BX3, boron trihalide. Now, what's going to happen mechanistically? What is BX3? Let's say Bi3, boron trichloride, boron tribromide, doesn't matter. I just call it X.
I mean, boron has
So it is a strong, yes, it's a Lewis acid, it's highly electrophilic. So where in that molecule, the cute little Fischer carbene compound, are electrons? Where is a nucleophile? No, the carbon is electrophilic in a Fischer system. The double bond, yes. I mean, one can argue that this has somehow got electrons, but where else? Oxygen. These lone pairs are sitting here waiting to do something. So what's going to happen? Let's figure this out together, step for step. What's going to happen? It's going to just coordinate, for argument's sake. Now, I can draw it with an arrow, or I can write it like this. No, something's wrong here. No, that's correct. That's correct. So, so instead of using a dative arrow, I can write it actually as a bond. Right? That's not so important. That's just a way of representing it. Now, what's that going to do? Well, think about it. Remember, in the Fischer carbene, there is a bit of there is a bit of double bond character in this carbon oxygen bond. But let's neglect that for the moment. If I put a Lewis acid on this oxygen, what's going to happen? Well, we're going to pluck it off, aren't we? Check it out. You see that? So this is now for argument's sake what we're going to get if it's not concerted. I'm doing it in an unconcerted way. This is just making a mechanism using arrows and logic, right? So what would we get? Well, we would get something like this.
Why does it fall to the bond with the arrow like that?
Sorry?
With the arrow like that, why does it fall to the bond? Comes from the back.
Because it's coming from the metal to the carbon, sorry. Sorry. So we're pushing electrons around. All right, so now that's just, this reaction is probably proceeding in a concerted way. But let's say, the point is I want you guys to try and figure this out, right? Using arrows, electrophiles, nucleophiles. What's going to happen now? Well, think about this. We've got a negatively charged, we've got a boron X bond here, and we've got an electrophile sitting on the carbon here, right? So, what's going to now happen, if you will, is we're going to have something like this. No, that's not correct. Sorry. See, arrow's going in the wrong direction. That's correct. Always goes from the nucleophile to the electrophile. So the X minus, so the BX is essentially going to attack this electron, because remember, if we pull this off, we're left with a positive charge on the carbon here, essentially. And we generate this. Now that thing is going to basically, that is a nucleophile, because it's got lone pairs on the halogen. It's going to attack this electrophilic carbon that we generate here as a sort of a purported intermediate. And what is the result of all that going to be? The result of all that is going to be simply be CXR plus BX2OR. A halo carbene. And this is called a halo carbene. So that's what Fischer wanted to do. And he wanted to do that again because given the already electrophilic characteristics of the carbon atom, introducing a halogen there could make it even more electrophilic, and he thought that would be cool. Now, luckily for him, and you sometimes have this in science, what he got was even better. So what happened? Let's look at that molecule. Molecules have personality. Is that carbene going to be happy, the carbon atom of the carbene? No, why not?
Well, not enough electrons.
Right. To start off with, it's electrophilic. And now you're introducing an electron withdrawing electronegative substituent, making it even more electrophilic. So the carbon atom says, you're stealing all my electrons, and I'm already electron deficient, go away. Go away. So it wants to desperately get rid of the halide. But we've tricked it into accepting the halide, so it's been tricked. And now it's stuck with the halide, but it doesn't want the halide. So the only choice that it has is to do what?
Give it to them.
Yeah, give it to the metal. And we lose carbonyl. X goes there, and this has been studied intensely, this reaction. And we get carbonyl. So, oh, sorry, I've written here chromium. Let's keep it N. So this is N is, remember, group 6 metal. Halocarbene. So the halocarbene is not stable, and boom, it goes all the way through to the carbine. All right, incidentally, this mechanism that I've presented here at the bottom is just something I've dreamt up. It could also proceed via a concerted pathway, but the reason why I've done that is because I want you guys to see that just from knowing nucleophiles and electrophiles, you can figure stuff out. Do you see that? And that's what chemists do. They sit down and they try and predict these things. They don't learn reactions. And then you can see it. So that's a prototypic Fischer carbine complex. It has very interesting reactivity. I'm not going to go into that today. Yes, what is the oxidation state? What is the, of that chromium, what's the oxidation state? See, in order for us to answer that question, we have to think about ionic counting, and I didn't want to do that. It turns out the oxidation state is 0. If you want to count it ionically, the Fischer carbide count is a plus, you count it as plus. I really don't want to discuss that. All you need to know is that, like with Fischer carbines, Schrock carbines are also low oxidation state. Very similar. Okay, so that's now how we synthesize a Fischer carbine. Now, of course, Schrock was also in the game. And Schrock liked working with the more reactive stuff. And so he was in the game, and in 1975, so 2 years later, he isolated the first example of a so-called Schrock-type alkylidine. So a metal-carbon triple bond. So you see, this was all happening in the 70s, right? And actually, when Schrock made this discovery, it was just when he had accepted his position at MIT. He was working at DuPont as a research chemist. And if you read this paper, you'll see it says at the bottom their current address, Massachusetts Institute of Technology. And he went on to win a Nobel Prize later. So you see, it's people that are doing the science. That's something that sometimes people forget. So what did he do? He made that compound. Basically, that's the X-ray structure taken from the paper. And you'll see that it is tantalum. And with these neopentyl groups, this is the single crystal X-ray structure. Here are the neopentyl groups. That's the tantalum carbine, very short bond there. And here's a lithium with, this is called timida, TMEDA, tetramethyl ethylene diane, TMEDA. This is basically just coordinating to the lithium. How did he make this? Right, let's look at how he made it. That's the X-ray structure. Actually, very simple how he made it. He was also very clever. The prototypic Schrock carbine, or alkylidine. We saw it this morning. There's the compound. Now you got that compound in a Schlenk tube. You want to make a triple bond out of it. How are you going to do that? What do we need to get rid of? We need to get rid of what, particularly? Yes, we need to get rid of that pesky H. So what are we going to do? We're going to deprotonate. Have you done deprotonation reactions in organic chemistry? Well,
just acid base.
You have strong bases like butyl lithium, tertiary butyl lithium. These are deprotonation reagents. And if you do reactions at low temperature, you can pluck off hydrogens. Deprotonation is very important in chemistry. We're going to discuss this next week when we're looking at cyclopentadienyl complexes again. But basically, you take a very strong base, Lewis base, and you deprotonate. Now, the reagent that he used is N-butyl lithium. That's N-butyl lithium. That's a deprotonation reagent. And if you deprotonate using N-butyl lithium, what you get as a product is this. And that's basically what he did. Now, you see I draw it there as a carbene with the lithium sitting here. But what he basically did is he added a chelating ligand, TMEDA, so that's what that thing is there to coordinate. So in the presence of, with TMEDA, and that basically comes and sits here, and basically it stabilizes the lithium, because it's a very, very reactive molecule, that. And so that's what he made. Now, I've represented it here in my scheme here as a carbene. This carbon-lithium bond is not really a bond at all. It's basically something like this. So it is a carbine, in fact. So he did a deprotonation from his prototypic alkylidine compound using N-butyl lithium, which can act as a deprotonating reagent. You generate, it's actually very straightforward, you replace the H with the lithium, and you basically get the compound. And if we look at the X-ray structure here, you can see that the tantalum carbon-carbon bond, so this bond here, or this bond axis here is quite linear, and that suggests that it is a triple bond, right? So a carbine. That was the first example of a carbine compound that he made. Does everyone understand that mechanism or understand the reaction?
Yeah, I just forget, why do you need TMEDA?
That's a good question, because it's a very reactive molecule, and to stabilize this lithium here, to stabilize it, you generally do these reactions with ligands, neutral ligands that can coordinate to it to stabilize it. It's purely for stabilization. I mean, if you do it without that, it's okay, but then probably you're not going to be able to crystallize it. You see, he needed to grow crystals. So probably if you do the reaction without a base, you'll get the same thing, but it will probably not be as stable. Anything else? Kunsulu, you're happy? Right. Everyone happy? All right. Now, there are other ways of making Schrock-type carbines. I don't want to discuss these two. I just want to discuss this one at the bottom here, this that he reported in 1982, because it's a very interesting reaction. Now, I don't want to overload you with thousands of reactions. Just out of interest, there are other ways of making Schrock-type carbines. You can access them by dehydrohalogenation, and also you can access them by reducing a Schrock-type carbene or alkylidine. But these are not important for this course. This one is important. So what he's doing here, beautiful reaction, is he starts with a tungsten-tungsten triple bond. Look at that, these compounds exist. So this is a dinuclear tungsten compound with a triple bond between the two tungsten atoms. And he reacts that thing over there. Right, this is the compound. The groups aren't that important, but O-tert butyl. He reacts that with this alkyne. Check it out. And it goes off the... I don't know why it does that. This projector screen is really... There. Everyone can see it now, right? Oh, yeah, there. So, this is the important reaction. He starts with a tungsten, ditungsten compound, and he does an alkyne metathesis reaction with an alkyne. And you get this. This is a Schrock carbine. So this is a tungsten 6 carbine, plus 6 oxidation state. Oxidation state is not too important. All I want you to know is that fission-type carbine has a low oxidation state, a Schrock-type carbine has a high oxidation state. That suffices for me. With carbines, I want you to know a little bit more, but I mean, that's not so important here for this level. Now, what's happening here mechanistically? What's happening mechanistically? How do I get from here to here?
Is it safe to say that both tungstens are electrons?
Well, actually quite difficult. It's much simpler than that.
Is it a
When we have multiple bonds, what happens? We saw it a moment ago.
So what?
2 plus 2 cycloaddition. 2 plus 2 cycloaddition. So let's look at that and what's happening in that reaction mechanistically. That's all. I don't need this anymore. All right, let's look at that mechanistically. So this is a way of accessing Schrock-type alkylidines for tungsten. Doesn't work in all cases, but I'm going to do it in a general way. Well, actually, I'm going to look at the actual synthesis. So he took ditungsten. This is what he took. These complexes are easy to make. They're pretty stable. I was going to devote a lecture to this, but I've decided to can it. So that is a ditungsten, that is a tungsten triple bond. Tungsten triple bond. You have them in chemistry. It's pretty cool. Much more interesting than boring triple bonds in organic chemistry because you have d orbitals doing the. You also have, by the way, delta bonds and stuff like that. You even have, just from the Department of Useless Information, metal-metal 5-fold bonds, quintuple bonds. It's amazing. So, there we have this ditungsten triple bond. Now we react this with something like that. What's going to happen? We're going to have 2 plus 2 cycloaddition.
Isn't it sterically hindered?
Sorry?
Isn't it sterically hindered?
It is sterically hindered indeed, but it's, the reaction goes. So this reaction doesn't work in all cases. It is very, it is kind of limited. But as a matter of fact, you're right. That's better. It is sterically hindered, but the one side is not so sterically hindered. What's going to happen? We're going to get a 2 plus 2 cycloaddition, aren't we? 2 plus 2. So we're going to get OT butyl 3, tungsten, OT butyl, and we're going to get now a double bond because, of course, we're starting with 2 triple bonds, yeah? And there's our H, and there's our butyl. Sorry, so you don't start with the bis tertiary butyl, you start with a, to come back to your question, you see it's asymmetric. It's asymmetric, so it's not sterically congested, it can fit in. Obviously, if it's too sterically congested, you wouldn't be able to do it. But it's still pretty amazing because this is a very sterically demanding group in any event. What happens next? Goes again. Okay, so now we're going to have the double bond sitting like this. What happens now? Goes again. Yes. 3 times. So, what happens now if it goes the 3rd time? The tungsten-tungsten bond is broken. So I generate, in fact, the products are that and that. So I generate two carbynes. Now this carbine that's generated here is completely unstable. It's absolutely unstable. It undergoes decomposition, dimerizes, and does all sorts of crazy stuff. This one is stable and you can isolate it. So that's the synthesis of, that's a very cool way of making a Schrock type carbine using alkyne metathesis, starting from metal-metal triple bonds. Incidentally, you have these sorts of systems here are very common with group 6 metals. So molybdenum, tungsten, also chromium. All right, does everyone understand this mechanism? Again, you know, one must take into consideration that in reality it goes backwards and forwards, backwards and forwards, backwards and forwards, you know, and depending on the fine electronic tuning of the compound, you can make it go all the way or make it not go at all. Remember, so just think about that. You've got to design it in such a way that it goes all the way, because look, we have to do 3 2 + 2 cycloadditions, right? So yeah, that requires quite some energy. Now, the last topic I want to discuss today, right, I think we've basically know how to synthesize Fischer carbines. We understand the mechanism, hopefully. Remember, the target was a halocarbene. And we've looked now at 2 synthetic strategies for synthesizing Schrock-type alkyladides. The one, the prototypic deprotonation from the prototypic Schrock alkylidine, and this involving metathesis. Now, the last topic I want to discuss today is alkyne metathesis. Turns out that this compound here is an active alkyne metathesis catalyst. Now, we looked this morning at the mechanism of alkene metathesis. We have the same thing with alkyne metathesis. Exactly the same thing. But let's look at the mechanism again, just to make sure that we understand it. Schrock. Yes, this is a Schrock type. This is as Schrocky as it gets. Okay? As my colleague Christoph Marschner says.
Are these catalysts also only Schrock type?
You mean, can only Schrock type complexes do alkyne metathesis? Very good question. You know, the sort of the prevailing general trend is that Fischer type carbines are dead ducks, and Schrock type carbines are very reactive. Now that's a bit unfair, but generally yes, they're Schrock type. Generally they're Schrock type. Now, although you can do some, you can do in fact some alkene metathesis with some Fischer type carbines, but yeah. But not alkyne metathesis. Alkyne metathesis, so CC triple bond metathesis, you need generally a Schrock type system. There might be 1 or 2 systems that are formally Fischer type, but generally you need a Schrock type system. Now, what's going on here? Let's suppose, now remember, as with alkene metathesis, we get different types of metathesis. We get catalytic alkyne metathesis, something called cross metathesis, ring opening metathesis, ring closing, all sorts of different variations on the theme. But the mechanism is the same. So what I want to look at today is ring closing alkyne metathesis again, because it's an important mechanism. It's identical to what we had this morning, but let's look at it again. This is the compound. That is our starting point. Now let's suppose I react this with this. This is a diene. This is a 1,6 diene, a 1,6 heptadiene. You see that? Is that the correct name? 1,6 heptadiene. Yes, heptadine. So what do we do now? What happens? Step 1. Yes. So this baby comes and sees the pi electrons see each other and they interact. So coordination. Well, not coordination. Basically, let's just go straight to the 2 plus 2 cycloaddition. Well, 2 plus 2 cycloaddition. We get O-terbutyl, tungsten, C. Different from the alkene metathesis mechanism we looked at this morning, because of course we're starting with a CC triple bond, right? So if you get a 2 plus 2 cycloaddition, you're going to end up with, you're going to have a double bond and a double bond, right? Does everyone follow? Right, so what happens next? Again. So, there's our tertiary butyl group. Now we move the double bonds into this position here. And what happens now? Again. Again, remember, you can go backwards and forwards, but it goes all the way in this case. Okay, well now what's going to happen, this is the key step, is actually that, check it out, this is now going to be eliminated. This is going to be eliminated as a side product. So we're going to generate that. We're going to generate that. You see, if you do the cycloaddition here, that falls off, that flies away. So that's an organic byproduct. And what are we going to be left with here? We're going to be left with, let me just, so that's alkyne product of the metathesis product. And here we're going to have now that's our intermediate. What happens now? Yes. Now we play the same game. Intramolecular 2 plus 2 cycloaddition. Tungsten. All right. There's our little house again. What happens now? Again, we get another 2 plus 2 cycloaddition. So now we have a double one there, and we have a double one there. What happens now? Another one. And now what do we get? What's going to happen? This is the key step. We're going to generate this one, and
Is it impossible?
yes, that is possible.
A ring with a triple bond?
That's not possible, yeah. Well, no. It is possible. It's just very constrained. Just very constrained. So. It would be a very constrained CC bond in the example that I've selected. But if the
Shouldn't it be a 5-member ring? You drew 6.
sorry, did I draw 6?
Yeah.
Yes. Sorry.
Oh yeah.
I mean that's kind of a ridiculous molecule, right? But it's in principle possible. So if I had a imagine this. This is very constrained. But if this was very long, very long, or if this here was very long, right? then it would be possible, because then it would be at least more preferable, because you'd have a very long chain here and it would sort of loop around at the end. You understand? So if the tether is very long, then it's not such a problem. Now, this is a very important reaction, because it turns out, and also incidentally, alkene metathesis, these are very important reactions because they're used in organic synthesis, right? For example, if you're making some crazy molecule and you're an organic chemist, for example, antibiotics and stuff like that, very often you need to do ring closing metathesis to close the ring. But yeah, that's so basically that's ring closing metathesis. And actually, a very interesting read. I mean, you don't have to read it. I'm not going to examine you on this, but I just want to show you what's very nice is Schrock, for his Nobel Prize speech, acceptance speech. You can get the his speeches on
Nobel Prize website.
So Schrock Nobel lecture. There we go. So. What's this now? Come on. I did have it here, just a second. Nobellecture.org. No. Where on earth is this? He has a PDF. He has a PDF associated with it. And it's really a nice read. Anyway, I don't know where the hell this is. I had it on my PC the other day. Oh, here it is. Nobel lecture. Oh, this thing is. Yes, so these are very important reactions, and this compound does alkyne metathesis, and we have ring closing and we have ring opening, we have stoichiometric, and it can also be done in a catalytic way.
I mean, when we did for alkenes, also works for alkynes, right? The stoichiometric.
Yes, absolutely. I just wish that. Well, it's funny that the projector's now not working again. Anyway, I just really, I have to find that. Schrock Nobel Prize lecture. So, yeah, I'm gonna find it. Yeah, there we go. There we go. There we go. This is what I wanted to show you. So there you see he's done a ring closing metathesis reaction. This is from Schrock's Nobel lecture, not one of my slides. This is directly from his lecture he presented in Stockholm, 2005. And, well, he uses here a ring closing metathesis to come back to your question, can these rings exist? Yes, they can. There you can see it. If the ring, it just has to be bigger. I mean, the ring that I constructed here, I mean, this of course wouldn't work, right? Because that's just impossible geometrically. but I just wanted to use that to demonstrate the mechanism. Here you can see the importance of this. It turns out it makes some important biomolecules, right? So this is a very useful thing, not just in inorganic chemistry, but it's vital in synthesis and in industry, being able to do this sort of thing. And in the same way as with alkene metathesis, we lose 2 carbons in the process, right? So you see what's happening here. We basically started with a diene, and we basically link them together. And yeah, that's basically how that works. Works with big ring systems, so you need a big ring system. The ring system is small, you end up with what I had. So I hope that convinces you. And for an interesting read, if you're interested, I highly recommend reading this very interesting lecture from Schrock. You don't have to do it, it's just very interesting how they developed the chemistry for this. As a last sort of point that I want to make, well, not really a point, it's sort of more fun. I'm particularly interested in these sorts of compounds. My whole PhD was on not carbynes, but the heavier homologs of carbynes. So instead of working with carbon, I work with germanium and tin. And the compounds I made just for interest, sticking with a Fischer tradition, just so you guys sort of know my background a little bit, is I made these complexes with iron. I work with iron, and I made electron-rich, cationic, carbine-like compounds where E is germanium and tin. And actually, remember at the beginning of the lecture we were talking about the halocarbene that's unstable? Turns out, if you do it with tin, you can isolate it. So these compounds are stable. Right, so you can make the tin analog. So basically what I did my whole PhD on was the ideas from carbon to germanium and tin. Now it sounds trivial, but it isn't, because for various other reasons, the bonding situation is very complicated with the heavy, they form very unstable pi bonds. So, but I could isolate this compound, right? And it's perfectly stable. It's got a melting point of like 190. So again, molecules have personality. Why could I isolate that one? After all, it's isoelectronic to what Fischer was trying to do. And then when he made the carbine, it flipped over to the metal. Why?
Is it the size? Yeah,
Size.
something has more orbitals.
Yeah, it's more diffuse. Yeah, yeah. That's a possibility. What else?
Perfect.
Electronegativity. But yeah, I mean, so the point is you can isolate that. And you know, the funny thing is when I was doing my PhD, right, I isolated this pretty quickly, like in the first 6 months. And I didn't realize, only until I was writing up my thesis, just how damn rare those compounds are, right? And you know what? It's so easy to go from here to here. You just pluck off the chloride. And then you get the first examples of, and these are Fischer type systems. They're absolutely Fischer type.